I'm going to try to zoom through some stuff real quickly here. Forward models. What we want to do now is what we call inverse models. This is a bit more difficult. And this is just an early tooth, a horse tooth that we sampled just to see what it looked like. And you can see here's some seasonal signal, summer, winter, summer, winter, summer. And what is that telling us about seasonality? That's telling you the isotope value of the tooth that you sampled. Okay? Well, let's consider this is a predicted model that Ben Passy collected. And so this data actually is 4 years of rainfall data from Midway Field in Chicago, published in IAEA. So it's just standard data. And what Ben did is said, well, we've done a bunch of histological sections on how we think tooth forms based on its increase in density. So teeth take a while to form, and enamel takes a while to form. You might think about it just like, say we have a cup of coffee. It takes a while to actually fill it up. And the way tooth enamel forms is about 25% of it forms, and very early on, and then over the next year or 2 years, depending on the animal, you might fill up the rest of that volume. But it's always completely mixed. So you're getting some mixture of time signal. And so this middle picture that I'm showing here is what this signal looks like if we would make it into a tooth. And the total scale is exactly the same. So this is really highly modified from that. Okay? Now, Ben, using inverse methods, Ben Passy, reconstructed this to look like that, which is pretty close to this initial value, but it's not the same. So I want to explore that, what it is. And so this is what I described. Okay, this just Ben measured the density of the tooth. This is a hippo tusk. Just measured the density of the tooth, or the fraction of phosphorus on a volume basis. And you can see that the initial value is about 25%, and then it takes about 50 millimeters of time, whatever that is, to form the rest of the tooth. It turns out that's about a year or 2 years. Okay? And then it reaches a final constant value. All right, so here's the mathematical problem. So now we're par C, par T, and we just have all of these chemical reactions to take place. No rate constants, no advection, no diffusion. Okay? So we lay down enamel like this, but we actually sample a volume that cuts across these appositional surfaces. All right, so this just is a mathematical way to describe it. Okay, it's good to think about how this mathematics can help you. Here's another example of tomography where we just measured the density. Here's fully mature enamel, okay, and here's the dentine. So this is this cross section. As we go further and further down the tooth, we get to less and less mature material. Here, the enamel and dentine are about the same density. And way down here, you can see that the enamel actually has lower density than the dentine. So this again is the same distance. So here we are also able to measure the density, okay, and then this is the sort of the photographic description of density. So we did some experiments, and this is an experiment of a rabbit. So here we take a rabbit, a pure C3, well, we have a pure C3 diet. We switch it to a mixture of C3, C4 grass, and then we switch it back again. And we measure its breath. Okay, this is the animal's breath and diet. And then the rabbit says, I don't like this food, I'm not going to eat. Okay, so this is the other problem. Sometimes they don't cooperate with your experiments. Is that true, Seth? The animals don't always cooperate?
And then they disappear.
Yeah. Well, this one didn't disappear. After 2 days, he gave up and said, okay, I'm going to eat that food that you gave me. And so he eats the food, and then we give him back the food he likes, and he's very happy. Now, okay, so the red line is the forward model of what tooth enamel should look like, okay, based on that it forms like that, okay, using this model, okay, only we use the parameters that we derived for a rabbit instead of a bison, okay. So we find that, yes, the enamel looks pretty much like it should, but notice that now the enamel is predicted to actually see the diet change, as it were, before it formed in terms of time, okay? So basically, we have enamel that originally had this value, and as it matured, it was dragged up to here during this distance of time, okay? Likewise here, this tooth started here, but was dragged down to here by all of this part of the time signal. So can we get it back? Okay? So how do we get it back? What you do is you go find a geophysicist who works on earthquakes and talk to them. And they'll be your friend and they'll say, wow, I never knew that I'd write a paper on a hippopotamus before. And they can do this, okay? And you might be able to do it too. It just takes like a whole class in inversion theory, which mathematicians love, and so do geophysicists. So you remember matrix algebra from, I don't know, whatever grade you took matrix algebra in. So this is just the description of the tooth in a matrix, okay? So here's our tooth again. Here's the matrix that describes the tooth, okay? Now this is, the model that we're describing is actually called the moving camera. And now we all have moving cameras where we take a panorama film, or take a panorama, and your camera re-puts it all back together again. This was actually first described in geophysics in the 1970s, and I really hope the guy who worked this out, Bill Menke, this is like his 4th textbook where he describes how to do this. I hope that Menke actually got some royalties on that, because it's in every camera today, and he worked out the math. But this is just an example of a photograph. This is a blurred photograph. This is a mathematically reconstructed photograph. Pretty darn good. Okay.